Yeah, so we'll finish today looking at the 10-dimensional models. So far the board, I'll try and do the same thing where I write on this little bit at the start. So we've looked at 3 models. The first was the simple model with one basis vector 1, where all the fermions are periodic. Looks quite hard to see on there, but okay. 1 and S. And then last week, Farid, we looked at this model with 1S and an extra basis vector, which I called zeta, maybe incorrectly, where zeta was half of the gauge fermions. It was 16 real gauge fermions. And we basically made some, I pretty much went through all of the important details of this model and showed that with these 3 basis vectors, we ended up having, we had supersymmetry. So we essentially had from this so we either had a non-supersymmetric model with the gauge group SO16 cross SO16. So this was what we might call an n equals 0, so a non-supersymmetric model, and then depending on a choice of GSO phase, we got E8 cross E8 with n equals 1. So what we saw essentially was that the supersymmetry, so whether we had supersymmetry, which means like if we have a gravitino in the spectrum from the sector S, whether that state is in the Hilbert space or not, is the easy way to check for supersymmetry. And we saw that state is projected for the choice of phase between S and this vector zeta. So basically the GSO projection on the sector S with zeta could project the gravitino, which means it could project supersymmetry and give you a non-supersymmetry model. And that would have been in the case +1. So the +1 relates to the non-supersymmetric case, and the -1 to the supersymmetric case. So we saw that GSO phase determined the supersymmetry, but it also determined the gauge group, because if you're now looking at the states from the sector zeta, you can project the states with S from the GSO projection with S, or not, depending on this phase. If the states aren't projected, so they are in the Hilbert space, then the states from zeta are actually what we'd say are additional gauge bosons. So they would have looked like this, or would look like this. So you act with the space-time fermion on the states of the vacuum related to this vector zeta, and that's an extra gauge boson because you have a vector representation in space-time because there's one space-time index there. So this state we said actually gives rise to the 128 spinorial a 128 dimensional spinorial representation, which we said it arises because it was 2 to the power of 7, where the 7 is because in zeta you have 8 fermions which are all Ramond, so they're all periodic. So there are 8 periodic fermions, complex fermions, 16 real ones, but 8 complex periodic, and so there's 8 8 Ramond vacua tensored together. So there is 2 possibilities for each one. So there's 2 to the 8. And then we said that the GSO projection fixes to be odd or even numbers. And so it splits into 2 to the 7 odd or 2 to the 7 even. And they're essentially your 2 spinorial irreducible representations, which are usually called the spinor and the Alonso, yeah. So yeah, they're the two spinor representations. And so these states could give you these extra gauge bosons, which these states would enhance the SO16 to E8 plus E8. And then we saw that we had a combination which was zeta plus 1 plus zeta plus n. So 1 plus zeta plus s. That gave you the other set of gauge fermions. So in this case, writing it in terms of complex fermions, we could say phi bar 9 to 16. And this is like just the other group of 8, and that gives you basically the same kind of thing. So you get, again, some additional gauge bosons associated to the state, which would look like this, basically. So they have 8 Ramond fermions, so 8 so in the vacuum you'd have 8 of these plus or minus, and these are phi bar 9 to 16. And again, these can enhance the other SO16 to E8. So if you have, whether or not this state's in the spectrum or not is, again, it ends up being determined purely by this single GSO phase. The GSO phase between S and zeta. So that phase basically determines all of the important information about the model. Okay. So we've basically talked about these 3 models in a bit of detail, but now I just want to talk generally about what else you could have in 10 dimensions and then summarize it a little bit. So so I'll write on this board. So if we remember, we have the rules, the modular invariant rules, also called the ABK rules. So what I want to do now is consider what other possible vectors, basis vectors you could add into your models to generate other models. So then it's going to be useful to think particularly about so particularly we want to consider the ABK rule associated to the dot product between basis vectors. So we have this rule. So again, I'm going to write it like this, where I essentially assume that all the boundary conditions are real. So there's only periodic and anti-periodic. And then this boundary condition becomes, sorry, this equation, the modular invariance requirement is that the dot product between 2 basis vectors is 0 modulo 2. Okay. So remember, this would be, for example, the intersection. So this would be something like saying the intersection between these. So another way of writing this, if you wanted to use set notation, would be like that the intersection between like 2 basis vectors would be 0, 2, 4, 6, 8, etc. complex fermions. Because complex fermions count with ones and real ones count with halves. So you could say, so this would be, if it was real fermions, the intersection would be like modulo 4, because the real fermions are halved. Okay, so so if we think about it like this, then any basis vector we add, it either has to have 0 intersection with like these kind of vectors, or it has to have intersection of 2, 4, 6, 8. Okay. For us to have world sheet supersymmetry, the psi mu, so the space-time fermion, so like psi mu, the boundary condition for psi mu in each basis vector would be the same. So well, yeah, so for all components of psi mu should be grouped together essentially. So there's no way we can add a basis vector that like splits up psi mu. So the only basis vectors we can add would be on the right, on the anti-holomorphic side for the phi bar. So if we just think in terms of complex phi bar, we can only add groups of these. So let's call any additional, let me just see, so so we can only add groups of these phi 1 to 16 and make them periodic, such that they have intersection of 0 mod 2 with the other basis vectors. Okay. So we're not going to derive all of the possibilities, because I'm just going to present you with the results of doing that. But you can kind of imagine, for example, you might want to add, let's say, some basis vectors like called Z1. You might start off doing this. Z2 is and then try and add these kind of things into a new basis, which we can kind of generally try and start with the vectors 1 and s, because then we can get supersymmetric models, and we know they're going to at least we can get modular invariance from these, and then we can just sort of add these additional vectors, so additional groups of 2, 4, or 8 or whatever periodic gauge fermions into this basis here, and then see which ones, so make sure the rules are all obeyed for the ABK rules, and then see which models we get. And so luckily we can just sort of present what happens if you do that on this in this table. So it turns out that some of the models are going to end up being the same. So for example, you know, if you have a sort of symmetry in the way you define periodic gauge fermions in the basis vectors, and you can swap them around, you might end up getting the same from one E8 factor as the other E8 factor, and then you kind of end up with the same model. But so here is the summary essentially of the results you get. So Z1, Z2, and Z3, I can write on the board. So Z1 is zeta in this notation. Z1 is what I called zeta, which was 5 bar 1 to 8. Okay, so the model So these are all of the non-supersymmetric ones, I think. I know, SO16. So I don't know where the E8 cross E8 and the SO16 cross SO16 aren't here, but we already explained those. So there should be, I guess, 1S and Z1, which is the same as the 1S and zeta that we looked at. That's the one that gives you the E8 cross E8 and the SO16 cross SO16. So this is all possible dimension 2 vector bases. Okay. So the Z1 was this. Z2, I think, is a group of 4. Yeah. So Z2 is, well, they defined as 5 bar 7, 8, 9, 10. But this won't be unique. This is just one definition, like one way of doing it, this classification. And then Z3, not totally sure what Z3 was. Z3 is this. Two. So that would be like 1, 3, 5. 1, 3, 5, 7. And then it goes all the way up to 50. That's all the odd ones. Right. So this is what, just as I said, one choice for the basis vectors that you can make. Okay. So, and then so this table as well. Yeah. So this is how this is where all of the other ones are. So okay. So dimension 2. This just means there's 2 basis vectors. So you can start off by saying, okay, how many ways can I choose 2 basis vectors? And then here is summarized all the choices of 3 basis vectors using the same notation for Z1, Z2, and Z3. And you see here, this is where we have the E8 cross E8 and the SO16 cross SO16. And we actually get that in a few different cases because ultimately these choices of bases are sort of degenerate. Like this choice 1 and this choice 3, 4, 8 are all the same model in the end. So one thing you could do if you want more practice of like using the rules and deriving the spectrum of models, you could look at this table and look at the basis here and try and show that you get this, like why do you get these gauge symmetries, for example, and that you could also look at the tachyons. So in some cases you have tachyons here, some cases you don't. So in all the supersymmetric models, so the E8 cross E8 and the SO32, then you don't have tachyons because the supersymmetry like S, the supersymmetry generator projects the tachyons. But also in the SO16 cross SO16, the model we talked about last week and a bit today, this also doesn't have tachyons, but all of the other theories do have tachyons. So you can kind of look at like understanding why that is and why it ultimately relates to the presence in the basis of the vector S. in this 10-dimensional like setup. So yeah, if you wanted more practice in 10 dimensions, you could look at these tables. So I can send you a link to that if you want. I'll put it in the Zoom for you to read now if you want. Okay, so that's pretty much what I wanted to say about 10-dimensional models for heterotic. Yes, I can put this table in the notes at some point, but I haven't done that yet. Okay. Right, I'll turn off this. Yeah, so if you just want to, a bit more practice with understanding how you quickly and sort of get the main information about a model from the basis and doing the projections and stuff, then you could look at that table. Bit of like homework. But the only so that the one other thing I want to say about 10 dimensions is now moving away from heterotic and saying something about type 2. So far everything we've done has been heterotic strings. So I'll just talk about type 2 superstring in the fermionic language. So if you remember when we talked ages ago about the heterotic string, what we did was we had a sort of supersymmetric, like world sheet supersymmetric theory on one side, the holomorphic side, but then we had essentially the bosonic string on the other side. So the anti-holomorphic sector doesn't have a space-time fermion, so it's has no world sheet supersymmetry. So the two sides of the heterotic string are different, and that's sort of why it's called heterotic, because it's a sort of weird combination of two things, of a supersymmetric and a non-supersymmetric Virasoro algebra. Okay, so the type 2 string kind of is in a way like you might think a very natural choice, where you essentially put world sheet supersymmetry on both sides. So you have in our notation, you can think of it like having so you have, like we had in the bosonic string on the holomorphic side, so holomorphic. So on the holomorphic side, you still have space-time fermion and then a bosonic operator in general, space-time operator. And then on the anti-holomorphic side, we're going to have now the same theory, but just with anti-holomorphic fields. Okay, so in some ways the theory is simpler. So now let's just I'll just try and quickly understand in the free fermionic language, like what's slightly different and how you would construct a model. So again, we have the same essential rules and everything. And you could actually start off with the base effect of 1, which is now it would just be written like this. Okay, it'd just be the basis vector with psi mu and psi bar mu. Well, actually, let me start off by putting the type 2 theory. So we'll start off with vector 1, but then let's say we want to have supersymmetry, and again we might assume from what we did in the heterotic theory that again supersymmetry would be generated with this vector, so the vector where this holomorphic space-time fermion is periodic and nothing else is periodic. And then what we would notice, so let's say that our basis was 1 in F. Well, one thing we notice straight away is that if we do 1 plus F, we get what? What do we get? What's periodic? Yeah. So psi bar mu. So this we can call, makes sense to call that vector. We call it F bar. So it's like F but on the anti-holomorphic side. So we don't need to put this into the basis because we can generate it as this combination. It's because 1 plus S just gives us it, so we don't need it. Wouldn't be in the basis, but it's there in the model as a sector. And so now if we could also, for example, now write we could now call 1, we could call that F plus F bar as well if we wanted to. So 1 in 10 dimensions is just having the two supersymmetry generators together. And actually, the language that's usually used in textbooks when you learn a type 2 theory, we can relate to this language here. So what we've got is actually this sector S, for example, we expect that to give us the gravitino again. We know that it's the sector where this holomorphic spacetime fermion is Ramond, and the anti-holomorphic is Neveu-Schwarz, so it's anti-periodic. So this is actually, you could call the RNS. This is what would be called the RNS sector in if you look in textbooks on type 2. And then S bar would be the NSR sector. That makes 1, so that's S plus S bar. So that's actually like Ramond. And then, of course, as always, we have the Neveu-Schwarz sector, or what would be like, we could maybe call 0, but this sector corresponds to NS. So this theory, the type 2 theory, will be generated by the model 1 and S, and that will actually give us 4 sectors: the NS-NS, the RNS, the NSR, and the Ramond, by looking at the states from each of these 4 sectors. Okay. So in a way, it's actually a simpler, it's quite a simple model in the free fermionic compared to the heterotic, slightly more complicated because it's got the gauge fermions. Right? So one thing we could also say is that because we have, so a couple of other things about having supersymmetry on this side as well, the other slight changes that you have. So before we had the math formula would be, remember, it was -1/2 on the holomorphic side because basically because you had supersymmetry, and that nudges up the vacuum energy to -1/2 plus the contribution to the vacuum energy from the periodic, so the degenerate Ramond states, which was what we usually, if we call the sector alpha, we would write it like this. and then plus NH. And then, so before we had a -1 here because the heterotic string doesn't have any supersymmetry, worldsheet supersymmetry. But now it does in the type 2 case. So actually, this is just going to be the same on this side now. Okay, so it's actually just a symmetric, it's a symmetric theory, so these equations should be the same. The other thing that we'd have to be careful about is when we do the GSO projection, we have to know that we have this spin statistics operator, the delta. So the delta now, so delta for a sector alpha now has to take into account that we've got the space-time fermion on both sides. So we have e to the I times alpha of psi mu plus alpha of psi mu bar. Okay. So now you have to look at both of the boundary conditions for psi mu. So if you look at this equation, for example, it tells you that delta of the vector 1. So what would delta with 1 would be, well, for 1 this is periodic and this is periodic. So that makes this +1 rather than -1 for heterotic, because in heterotic you've only got psi mu. So you'd only have 1 here that would make this e to the I pi, and then now we've got 2, so this is e to the 2 pi I. So it's +1. Okay, so it's only these two. So this points to the fact that the sector 1, or the Ramond sector, is bosonic. It's a space-time, but gives rise to space-time bosons. So the space-time fermions come from the RNS and NSR, because here you've only got one of these two periodic. So these are the fermions. Okay. So there's not. I don't want to say too much more about it. I just wanted to make this connection to type 2. And I mean, one thing we could say. So I'll maybe very quickly summarize how you would see the states. So we know this is the basis. So then what we could do is write this NS. So this would be like the sector 0. So 1 plus 1. Here we obviously expect there to still be the gravitational state, so like the graviton and the dilaton and so on. So here we still have, so from the heterotic theory, we'd have the anti-holomorphic bosonic operator here. So that would nudge up the mass by 1 to make it massless. But in the type 2 case, you would just act with another the space-time fermion on the anti-holomorphic side. And this would give rise to your like 2 tensor representations that give rise to the graviton. So maybe more important, or importantly, you could look at the RNS. So that's the S sector. And as I said, like we expect this to be the graviton, right? And or sorry, the gravitino. And in the heterotic theory, we had a bosonic operator, but now we just have to nudge up the mass by half. So the gravitino actually would be just given by having anti-holomorphic operator with the space-time fermion on the so the like plus minus for prime mu from S. So this states spin 3/2 still, because this is spin half, this is sort of spin 1 vector. And what we do is we could do the projection with 1. So we could do, if we did so you can check this if you want. So if you tried to do the GSO projection with the vector 1, well, what would it do? It would act on, so it's periodic in everything. So this and this. What it would end up doing is essentially, it would be plus or minus 1. And what it would do is it would fix this. This would become 4. What we write as 4 even or 4 odd, which just means that there would be like, this is like what we were saying about when we did the SO16 and the E8 about the spinor representations decomposing. So this is like choosing this is also called choosing the chirality. So the chirality of the spinor, the overall chirality. So it's like an even or odd number of minuses in the vacuum, depending on the choice of this GSO phase. So that's what the projection. So if you just did the GSO projection with 1, you would end up choosing between 4 even or 4 odd for the vacuum related to S. Okay, so I think off the top of my head, plus 1 would probably be odd, I think. So I think plus 1, because this is periodic, then this would then have to be odd. So this would be like 4 odd for this vacuum, and this would be 4 even. You can check that doing the GSO projection. And so in the type 2, this is actually what we might call, I can't really remember which way around it would be, but one is the type 2A and one is the type 2B. So the distinction between type 2A and type 2B is essentially wrapped up in this definition of the chirality of the gravitino. So type 2, I could check fairly easily which one it is, but let's say this is, I can't quite remember, but one is type 2A, one is type 2B. Let's just get that. So you would also get a similar thing for if you did the NFR. So the NFR sector, which was this F bar, you would end up finding that this same phase determines the chirality of the gravitino from here. So this also has a gravitino. Just with the where you're basically swapping around, because you've got the anti-holomorphic to the holomorphic and things are swapped over. But again, this C1S, this turns out to be the phase that determines the chirality of this gravitino. And again, you can check that you get something like, again, you fix the odd or even number of minus signs in this vacuum, and that's your distinction between type 2A and type 2B. These just odd or even here and here for the Gravitini, basically. And we could, yeah, the Ramond sector, if you think about it, so the Ramond would be 1. That's Ramond. And this would be like F crossed with F bar. And so this is spin half, this is spin half. So this is if you take 2 spin half representations, then it should turn into like a vector and a scalar, or some vector and some scalars, depending on what sort of degeneracies you have. But so you should get vectors or vector and then scalars. And obviously this is good because we knew that the Ramond sector should be bosonic. But yeah, I mean, in type 2, this is where the Ramond sector is sort of significant, because you have to, I mean, one thing is the states from the Ramond sector in type 2 are really originate from D-branes, and not the fundamental string. So you have to go into branes and stuff. But also the thing another difference about type 2 that I'm not going to talk about is that type 2, you can have open strings, whereas heterotic, we were always like implicitly talking about closed strings, which are strings where like the boundary conditions are like so this kind of thing. So you close the loop on the string. So in heterotic, you can only have these closed strings, but in type 2, you can have open strings. So open strings would be where essentially these two the boundary condition here as opposed to here, they don't have to meet up. They can be defined essentially in terms of like you can attach the strings onto branes and stuff like that. And that in type 2, because one thing you can notice from this analysis we've just done is, well, you haven't got the gauge fermions, right? You haven't got, as we had in heterotic, we had some gauge fermions, the phi bars, and the phi bars allowed us to easily build a gauge group, which generally was like a rank 16 gauge group in 10 dimensions. And in theory, what you do in heterotic is then you go to 4 dimensions and you use those gauge fermions to generate you a gauge group, which is at least you can contain the standard model gauge group in it. But in type 2, you might be like, well, where does the gauge group come from? Because there isn't any gauge fermions. We can get the gravitational states like the graviton and the gravitini, but where's the gauge sector? And in type 2, you get the gauge sector from the open strings, which we're not going to be talking about, but the open strings attached to branes, and then different choices for how you attach them to branes can be associated to gauge groups. Okay, but yeah, it was just I think good to make a connection to type 2, because you see obviously other people work on type 2 strings, and you can at least see how it would look in the free fermionic language. Okay. So that's a very brief overview of the type 2 case. I don't think I had much else to say. There was one thing, which is that, okay, well, what if we'd only taken 1? So what if we didn't have S? We'd just taken 1. So that would be like having a theory with the NS-NS sector and the Ramond-Ramond sector. because there's no S to make these Gravitini or anything. So if you just had one, you would expect there to just be like an RR and an NS and F. So these are bosonic, so purely bosonic theories, and obviously, so no supersymmetry. And so this theory is not particularly interesting. We would, as usual, this phase 1-on-1 is free to be chosen as plus or minus 1. This choice plus or minus 1, this is the only freedom in the theory because there's only one basis vector. So this theory is actually what we call type 0. So type 0 because it's 0 supersymmetry. And so this is the type 0A and the type 0B. Depending on that choice of the C11 phase. Okay. I think there's pretty much it for type. So I think that brings to an end all of the 10-dimensional stuff I wanted to say about superstrings. So we've done the classification, or you've seen essentially the table that summarizes the full classification of the heterotic string in 10 dimensions. And maybe I didn't say this clearly, but in 10 dimensions, there wasn't actually that many choices. Even though there was like quite a long table, a lot of the choices corresponded to the same string theories, the same gauge groups and so on. And actually there was only, I think, 7 choices for the gauge groups. So you have the supersymmetric ones, the E8 cross E8 and the SO32. And then you have the SO16 cross SO16, which was the one that's non-supersymmetric but doesn't have tachyons. And then you have some tachyonic theories, which were things like the SO8 cross SO24 and the E7 cross SC2 all squared. So there's these theories which are all tachyonic, so they are fundamentally unstable. So usually people only talk about the SO32 or the E8 cross E8, the supersymmetric theories, and sometimes it's increasingly common now to also talk about the SO16 cross SO16 because it's also tachyon free. But so these are the three main heterotic strings that you see talked about a lot. The other ones, because they're tachyonic, tend not to be discussed that much, but they're still important. And we've been interested in them in recent years with Alon, and other people have become more interested in them recently. There is one theory which I didn't talk about. Sorry, there is one theory that wasn't mentioned on that table. So there is one heterotic string that is a weird one that you don't generate in the normal way using the normal types of basis vectors. You have to be creative and use, we talked about these necessarily real fermions and things to generate, you can generate a theory with a single E8. So rather than E8 cross E8, you can generate a theory with a single E8. And that's sort of the final heterotic string in 10 dimensions. And that was sort of is usually discussed, but it is interesting because it's all of the other theories have rank 16, so the groups are all rank 16 in the sense that SO16 cross SO16 is rank 16, so is SO8 cross SO24, so is E8 cross E8. But in order to get a single E8, you have to break the rank of the gauge group, which would correspond essentially to projecting out certain Cartan generators. So the Cartan generators, remember, were the ones, the diagonal ones. So they were the ones that were like from the NF vector heterotic. We have these Cartan ones, which would be the ones like Psi mu, and then the two gauge fermions would have the same, they'd be the same ones. So it'd be like I and I, and then maybe with a complex conjugate. But basically, they're diagonal in the sense that they, if you just did them across in terms of I and J. So in general, this might be J, but in the Cartan gauge bosons. So remember, these are the gauge bosons from the Nebel-Schwarz sector. So these are the Cartan ones. So usually, in order to, in all of the usual types of basis vectors that we've discussed, these will always be there. Because if you look at the GSO projections, it's very hard to project these out. You have to use sort of weird basis vectors, still obey the rules, but basically you have to use, I think, necessarily real fermions or different groupings for the fermions. So the E8 was the only one where you could actually project out sort of half of these Cartan generators, and only leave 8 of them which generate the E8. And that actually takes into the realm of like a completely different kind of Lie algebra, which would be related to what's called the Catch-Moody level 2. So usually what we're talking about is a level 1, and this, in order to project out Cartan generators like these states in the model, you need to go into a higher level Catch-Moody algebra to do it. And generally, you will never really need to worry about that, but I just wanted to mention it for completeness, so that you know that there's the two supersymmetric theories from the heterotic string. There's the non-supersymmetric one that has no tachyons, SO16, cos SO16. Then there's the tachyonic ones, including this E8 one, which is this strange one where you use higher level Catch-Moody algebra thing. So, and then I just wanted to mention this connection to type 2, so you see also how type 2 would work. And now next week we'll start doing 4 dimensions, 4-dimensional models, and then we can start gradually. We'll get to, in a couple of weeks, we'd probably be at doing more phenomenological models, so we can start looking at more things related to physics. At some point, I'm going to also do something more about partition functions, and something about like maybe a bit more about the Lie algebra stuff and the group theory, because sometimes we have to interpret states, and that requires us to know some basic stuff about representations of groups and Lie algebras. Okay, but that's it for today. If you've got any questions, just type for Reed if you can't speak.